Okay, so let us begin. Proved this last time that an M module has a composition series if and only if it satisfies both ascending chain condition and descending chain condition, and earlier we proved that if M has a composition series, then every composition series will have same length. So, when if M has a composition series, then M is called a module of finite length not only that, this finite length, there is a unique integer associated with M, which is the length of any composition series of M, and length of a composition series of M is called the length of M, denoted by, there are L of M. Okay. This is uniquely determined because of the theorem that we proved earlier, that any composition series can be will be of same length. So, this length is unique. For example, we have already seen what is so if I take, let's look at this kx mod x square. Let us look at this M to be, this is a over kx itself, you can think of A to be kx itself or k itself. Then you have M or kx mod x square ideal generated by x mod x square contain 0. What is this? Can you tell me what is ideal generated by, this x mod x square okay. So, this is an exercise. If I have a ring A and an ideal and an element A in A, which is a non-zero divisor, what is meant by non-zero divisor? That Ax is non-zero for any non-zero x in A. Okay. Then this is isomorphic to what? Isomorphic to can you looking at this, are you not tempted to do something? Right? Try to see if you can prove this. Okay. Suppose you want to prove this, how do you go about doing it? From where to where? From here to? Send a map A going to multiply, x going to Ax bar, and look at what is the kernel. Okay. So, because of this, what would this be? Suppose this is true, x is a non-zero divisor in Kx, right. So, if I assume this is true, then what is this? This is same as x Kx, ideal generated by x square is x square Kx, no, that is same as this. So, this is isomorphic to Kx mod ideal generated by x, but what is Kx mod ideal generated by x? K. So, this is a maximal submodule of this. This is a maximal ideal here, x ideal generated by x is a maximal ideal here. So, this is a simple, this modulo this is simple. Similarly, this Kx, this is say isomorphic to Kx mod x, which is K, which is a simple submodule, right. You do not have any Kx submodule of K. So, therefore, this mod this is simple. So, what is the length of M here? What is the length of M? 2, right. So, now what is length of Kx mod x power n? What is length of n? Prove this. Oh, not factorial n. Okay. Okay. So, now let us look at yeah. This is So, how do you say this is M2 contained in M1 contained in M0 equal to 0, right. When do you say this is a composition series? If M2 mod M1 is simple and M1 mod M0 is M1 mod M0 is M1 itself. So, M1 should be simple and M2 mod M1 is simple. Now, what is M2 mod M1 here? M2 mod M1 is Kx mod x square mod x Kx mod x square, which is Kx mod x, which is K. It is a simple submodule. Any vector space of dimension 1 is a simple submodule. Particularly, we are looking at modules over Kx. So, it does not have a proper submodule Kx a submodule contained in K, right. So, therefore, this, because every element is a unit, if you take any element and a submodule generated by that, it will have to contain K, complete K. So, K is a simple, any field is simple module over itself, right. So, this is M2 mod M1 is simple. Now, look at M1, M1 itself is Kx mod x, which is K again. So, this itself is K, isomorphic to K, therefore, this is also simple, therefore, M1 is simple, therefore, this is a composition series. Let us look at some properties of length. Okay. Let M prime M double prime be modules of finite length. Okay. Suppose 0 to M prime to M double prime to 0 is an exact sequence. let us reserve the conclusion. Let us look at what we can say about lengths. Okay. What can you say about, so suppose I have a, so I can think of m prime as m prime is isomorphic to a submodule of m, right. So I can as well assume that m prime is a submodule of m. Similarly, m double prime is isomorphic to m mod m prime, I mean m mod image of m prime. So I can assume as well assume that m double prime is indeed m mod m prime, with m prime a submodule of m. Okay. Now suppose I have a, so m prime is a submodule of m. Now I have so this is m naught prime contained in m1 prime up to mn prime. This is m prime. This is a, suppose this is a composition series of m prime. Think of them, so m prime is a submodule of m, so all these are submodules of m as well. So therefore these all will be, these all will be submodules of m, and this will be a composition, a part of composition series of m itself, right, because each of them is submodule of m and each quotient is simple. Okay. Simple module does not really matter whether we are thinking of a submodule of m prime or m. If it is simple, it is simple. Okay. So this will be a submodule of a composition series of part of composition series of m. Now look at let's look at composition series of m double prime. M double prime is m mod m prime, right. So this I will call this as mm double prime. I have a composition series like this, m1 double prime contained in m naught double prime, which is 0. Now what is m naught double prime here, which is 0? What is meant by 0 here? M prime mod m prime, right. Now if I look at m1 double prime, it is a submodule of m mod m prime. How does any submodule of m mod m prime look like? No, forget about composition series. How will this look like? This will be a submodule of m mod m prime, right. How does any submodule of m mod m prime look like? So it will look like something of the form m1 mod m prime, right. So this is m prime mod m prime. Now the next one, so m2 double prime, this will look like m2 mod m prime, and so on up to this is m mod m prime, right. Now look at this quotient m1, I mean m1 double prime mod m naught double prime. What is that? This is same as m1 itself. m2 mod m1, m2 mod m1 is same as m2 mod m prime mod m1 mod m prime. Therefore that is simple. m2 mod m1 is simple. Similarly, M3 mod M2 is simple, up to M mod MM minus 1 is simple. So, what does that give you now? So, you start with 0 here, go up to M prime, from there you jump to M1, M2 and so on up to M. That will be a composition series for M. So, what have we shown? Length of, yeah, so length of composition series is called as length of the module itself. So, length of M is equal to length of M prime plus length of M double prime, right. So, let us write down that first. So, let this be a composition series of let this and this be composition series of M prime and M double prime respectively. So, there we can say without loss of generality, we assume that M prime is a submodule of M and M double prime is, so here without loss of generality we may assume, we proved this last time? Oh, I thought we proved only, we ended with, oh, we proved that.
The statement was not written, we have already.
Oh, okay, okay. Fine. So, we, okay, then let us, okay. So, this is a, then this will be, you know, M naught prime which is 0 contained in M1 prime contained in up to Mn prime contained in M1 MM is a composition series of for M, and that gives the result. For k vector spaces, this is for finite dimensional k vector spaces. The following are equivalent. V is finite dimensional V has finite length, V satisfies ascending chain condition and V satisfies descending chain condition. All these are equivalent. So, what we are saying is that length is nothing but generalization to the case of modules analogous to the dimension of a vector space. Okay. So, this is, if this V has finite length, so we are talking about V as a module over K. 2 if and only if 3 and 2 if and only if 4 we already know. Okay. If 1 implies 1 if and only if 3, 1 if and only if 4 directly follows from linear algebra. Because any subspace is of finite dimensional. So, you start any ascending chain or descending chain, it has to terminate. Each step will in an ascending chain, each step dimension will increase at least by 1. So, it cannot go more than the number of steps as much as in the dimension of V. You start with 0. Similarly, for any descending chain, you can have at most dimension V number of steps. So, 1 if and only if 3 and 1 if and only if 4 is straightforward. So, we only have to prove 1 implies 2 is again straightforward. Why is that so? If it has a finite dimensional vector space, I can take a basis V1, V2 up to Vn, then you can have a composition series V1 up to Vn contained in containing V1 up to Vn minus 1, containing V1 up to Vn minus 2, and so on up to V1 and then to 0. Each quotient will be isomorphic to K, it will be a one dimensional vector space. So, therefore, it will be simple. So, therefore, 1 implies 2 is a basis, then so 0 K span of is a composition series for V has finite length. And we have already proved that 2 implies 3 and 2 implies 4 has already been proved, because a module has finite length if and only if it satisfies both ACC and DCC. So, 2 implies 3 and 2 implies 4 is already proved. So, on vector spaces, finite dimension is equivalent to saying that it is finite length, which is equivalent to saying that ascending chain condition, descending chain condition are all satisfied. So, see what we are seeing is that if a ring suppose your ring is Noetherian, okay. When can we say that length, this has a composition series? Can we say, suppose we have some nice property is true, can we say length of A is finite? Okay. We know that this is not always true. For example, Z, Kx, or take Z, it does not have a composition series, right, because you take you start with any ideal, there are no simple submodules of Z. You take any submodule, it contains a proper submodule. For any nz, you have infinitely many chain. Starting with any nz, you have infinite chain descending. So, descending chain condition is never satisfied in Z. So, length of Z is infinite, or it does not, it is not a module of finite length. But can we say something nice if if suppose with some nice property, suppose suppose A1 up to suppose you have M1 up to Mn be maximal ideals of A with zero equal to the product. The product of the maximal ideal is 0. For example, suppose you take Z6. What are the maximal ideals of Z6? 2 and 3. The product is 0. So, if you have some nice structure on A, okay, the product is maximal ideal. So, product of maximal ideal is 0. Then look at this sequence contained in M1 up to Mn minus 1. What can you say about this? What is this a simple module? Forget about this part. What would be this mod this? No, this modulo this. See, if I call this ideal or ideal I, this is nothing but I mod Mn I, right. This is a module over A mod Mn, or in other words it is a vector space. If it is of dimension 1, then we will have the previous proposition will say that it has this is simple, or whatever it be. If I look at this mod this, it is a vector space over A mod M. So, it will have finite length. Okay. Now, this need not be simple, but this has finite length. I mean this is a finite, this satisfies ascending chain condition, or it has finite length. Now, look at M1 up to Mn minus 2. This 0 to M1 up to Mn minus 1, you have this inclusion map M1 up to Mn minus 2 to M1 up to Mn minus 2 mod M1 up to Mn minus 1 to 0. Okay. This, see this by induction, this is a module of finite length, not by induction. This we have seen that this is a module of finite length, because this modulo this is a finite dimensional vector space. So, here okay, why is it a finite dimensional vector space? We are making use of the fact that this is Noetherian. What is this? If I, this is I mod Mn I is a vector, it is generated by generators of I. I is an ideal in a Noetherian ring. Every submodule is finitely generated, or every ideal is finitely generated. So, therefore, this is finitely generated. Therefore, this has ascending chain condition, because your vector space is this modulo this. So, this itself is a mod mn vector space, it has finite length, which is equivalent to saying that it is finite dimension is equivalent to saying that finite length, it satisfies ACC, it satisfies DCC. So, this has finite length. Similarly, this is a finite dimensional vector space over A mod mn minus 1. So, therefore, this satisfies DCC, ascending chain condition, descending chain condition by the previous proposition. So, in the when we proved that length is additive, what we proved is that if I have a composition series of this and if I have a composition series of this, I can just merge them and get a composition series of this, which means this length is finite. I can keep going up to, so now keep going to M1 and then contained in A. So, I have this 0 equal to M1 up to Mn, M1 up to Mn minus 1, M1 to A. What we are showing here is that this is 0, this has finite length, this has finite length comes from the fact that this is a finite dimensional A mod Mn vector space. By induction, the next one, or by recursively taking it to the next one, this has finite length, M1 has finite length, and therefore A has finite length. Okay. So, if A is Noetherian and M1 up to Mn are maximal ideals with their product being 0, then length of A is finite. Yeah.
Product of all maximal ideal or some maximal ideal?
I mean some maximal ideal, they let this be maximal ideals, okay, be some maximal ideals, need not be all maximal ideals. See, if we are not making use of that fact, I mean just there should be maximal ideals whose product should be 0. Then you can have a, this is not a composition series, by the way, this need not necessarily be a composition series, because this, yeah, sorry, yeah, I mean I just wanted to make clear that we are not emphasizing that product of all maximal ideals. I mean a priori we do not need to say that. So, what we have shown here is that suppose M1, M2 up to Mn be maximal ideals of R, maximal ideals of A, such that M1, the product M1 up to Mn is 0. If A is Noetherian, then A is Artinian. Okay. It satisfies the descending chain condition. What about converse? Suppose A is Artinian. Okay. again we can look at the, see here what we are saying is that each quotient, look at this one, this mod this is an A mod Mn vector space. Okay. Therefore, what we are saying is that since this is finitely generated, it satisfies DCC. Conversely, see once we are looking at M1, look at any Mi mod M1 up to Mi plus 1. This is a vector space over A mod Mi plus 1, right. So, this one satisfies ascending chain condition if and only if, descending chain condition if and only if this is of finite dimension, if and only if it is of finite length. So, on this module all these are equivalent. So, therefore, we can swap the roles of ACC and DCC in this argument, that this mod this is a finite is a vector space, therefore, it satisfies ACC if and only if it is DCC. Now, look at the next one, this mod this is a vector space over A mod Mn minus 1, therefore, this satisfies ACC if and only if it satisfies DCC. Keep going. So, ultimately what we get is A satisfies ascending chain condition if and only if it satisfies descending chain condition, or in other words A is Noetherian if and only if A is Artinian. So, what we have proved is more than this. Let me modify the statement. Then A is Noetherian if and only if A is Artinian. Okay. So, this you should write down the complete proof. Okay. It is I mean it is the same, we have not just that I have not systematically written down, but you should be able to do that. So, a ring A is Noetherian if and only if every A satisfies ascending chain condition, every ideal is finitely generated, and every chain of every collection of ideals of A has a maximal ideal maximal element. Okay. Now, if A to B be an onto ring homomorphism, or in other words, let us to start with, let I be an ideal of A. Okay. If A is Noetherian, then what can you say about A mod I? Yeah?
It
A mod I will also be Noetherian, right, because every ideal of A mod I looks like some j modulo I, where j is an ideal in A containing I, but j is finitely generated. So, if I take those generating set and look at their images in A mod I, that will generate j mod I, right. So, therefore, every ideal of A mod I is finitely generated, therefore, this is Noetherian. Okay, property 1 maybe or observation, remark, whatever. As a corollary of remark 1, one can say then so let me be an onto ring homomorphism. If A is Noetherian, then so is B. If I have a ring homomorphism onto ring homomorphism, then B is isomorphic to, so let me just say B is isomorphic to A modulo kernel F, right, first isomorphism theorem. B is isomorphic to A mod kernel F. If A is Noetherian, then A mod kernel F is Noetherian, which means B is Noetherian. Okay. Suppose, so if B is, if A is Noetherian, and B is finitely generated, B is a ring which is finitely generated A module, then B is a finitely generated A module. How do you say this? So, here to say that it is a, okay, this is a Noetherian ring. See, as a ring it is Noetherian, we want to say. See, as a mod, that we have already seen. See, if A is Noetherian and B is finitely generated A module, then we have already seen that it is a Noetherian module, Noetherian A module. But we want to say that as a ring it is Noetherian, right. So, how do you do that? We have many ways of saying this. We want to say that every, let us say for example, every ideal is finitely generated. If I take an ideal in B, it is an A module, right, but B is already a Noetherian A module, therefore, this ideal is finitely generated as an A module. In particular, it will be a finitely generated B module as an ideal. See, if I take, okay, yeah, so I am looking at A contained in B, or A, yeah. And we need to have multiplication compatibility structure. So, if I is an ideal of B, then I is an A module. This implies that I is finitely generated A module. What does that mean? So there exists a finite generating set, let us say x1 x2 up to xn, such that every element of I is written as a linear combination of the form a x1 plus a1 x1 plus etc. a n xn, where each ai is coming from A, but A is already there in B. So therefore it is a every element is a linear combination of x1 up to xn, which means I as an ideal is finitely generated, right. So which means in I such that each A in I is of the form a1 x1 plus etc. a n xn with ai in A, which implies ai's are in B, and that implies every element of I is a B linear combination of this same set x1 up to xn. Which means I is a finitely generated ideal in B, implies B is Noetherian. Okay. If A is Noetherian and S in A is a multiplicative set, then what can you say about S inverse A? How does any ideal of S inverse A look like? S inverse I, where I intersection S is empty, right. Now I is an ideal in A is Noetherian, therefore it is finitely generated. So therefore S inverse I is also finitely generated. So this means this is Noetherian. So now comes the question, A is Noetherian K is Noetherian, any field is Noetherian, it has only two ideals, so every ideal is finitely generated. What about Kx, is it Noetherian? Noetherian, ascending chain condition, or finite, every ideal should be finitely generated, is that true? Kx, Kx is PID, right, it is a principal ideal domain. Every ideal is generated by one element. So therefore this is Noetherian. What about, yeah, every PID is Noetherian. What if I put Kxy? Here we know, and we do not know anything about this, right. Can you think of, given any n, my exercises for each n in n, find an ideal I n in kxy generated by n elements. That means, however large your n is, 10 million, whatever it be, the ideal is generated by, there exists an ideal generated by that many ideals. So, are we thinking that this is not Noetherian? Are we saying that it is not Noetherian? We will see it in the next class.